Scientists believe that in each of us there are 10,000 billion atoms in our lungs. That's a 1 with 22 zeros after it, just in our lungs. Now think about this. Every breath from every person that has ever lived contained atoms, atoms that were part of them. Hundreds, thousands, millions of years later, those atoms are now in your lungs. In fact, your whole body consists of the atoms that once existed in every person that has ever lived.
Usually, when an organism dies, it quickly decays and breaks down into small chemical bits that disperse in the environment. The essential atoms of biochemistry, including carbon, oxygen, nitrogen, and more, are recycled. These atoms are used over and over again. It's amazing to think that the majority of atoms in your body were once part of trilobites, or dinosaurs, or even those earliest living cells. Those creatures died. Their atoms became part of the soil or the air, and now you eat food and breathe air made of those same atoms.
Picture an atom. What does it look like? Most likely it will resemble something like this. A fairly large nucleus surrounded by orbiting electrons whizzing around the nucleus. This image is a popular icon of the atom, but it only vaguely represents our current model of what the atom looks like. Matter is made up of tiny particles called atoms that cannot be divided into smaller pieces and cannot be destroyed. He also stated that all atoms of the same element will be exactly the same, and that atoms of different elements can combine to form compounds. The really awesome thing about Dalton's model of the atom is that he came up with it without ever seeing the atom. He had no concept of protons, neutrons, or electrons. His model was created solely on experiments that were macroscopic, or seen with the unaided eye. Now let's fast forward to the late 1800s when J.J. Thomson discovered the electron. He decided that these particles must have come from somewhere within the atom, and that Dalton was incorrect in stating that atoms cannot be divided into smaller pieces. Thomson went one step further and determined that these negatively charged electrons needed something positive to balance them out. So he determined that they were surrounded by positively charged material. This became known as the plum pudding model of the atom. The negatively charged plums were surrounded by positively charged pudding. A few years later, Ernest Rutherford, one of Thomson's students, did some tests on Thomson's plum pudding model. The members of his lab fired a beam of positively charged
is a nucleus. This is made up of even smaller or subatomic particles called protons and neutrons. The protons each carry a positive electrical charge. The neutrons are as heavy as protons but carry no charge. This means that overall the nucleus is positively charged, and orbiting around it are negatively charged particles called electrons. The size of the negative charge carried by an electron is equal to the positive charge carried by a proton. Now the electrons are moving at incredible speed, in fact 3/4 of the speed of light, so what stops them shooting off in any direction? If we could pull an atom apart into its components, we'd see that a neutral atom has the same number of electrons as protons, and it's the force of attraction between the positive and negative charges that prevents the electrons escaping. Each type of atom is identified by the number of protons and electrons it has. A hydrogen atom has just one proton and one electron. An oxygen atom has 8 protons and 8 electrons. An iron atom has 26 protons and 26 electrons. But this is not enough to explain the behaviour and properties of most substances.
It may sound like a bunch of gobbledygook. It was the insight necessary to understand how an object can be both a particle and a wave. This single statement led to the understanding that subatomic particles can disappear and reappear in another place. And they can do this without existing in the intervening space. When an electron is trapped inside an atom, the places it can disappear and reappear include specific locations around the nucleus. And that makes it look like a shell. Basic particles can also be in more than one place at a time, if the time is brief enough. An electron can travel from here to there along all possible paths simultaneously. And even more astounding, these particles can appear out of the nothingness of space, exist for an extremely brief instant, and then disappear.